Alright guys, so in that particular video you saw the seismic dampers and how they were lessening. The one on the right really lessened the effect of that seismic wave, the shake board, and the one on the left hand side was really moving because it did not have any of these seismic dampers incorporated into its construction. So for structural design, we talk about stiffness and flexibility. The taller a building is, the more flexible it is. The reason behind this is it's tall, so it has more space or more height to get rid of or dissipate the energy that's trying to move through it. Okay, my example here in parentheses is try thinking of bending a short metal rod versus a very long one. Okay, so that the longer it is, the more flexible it will be because, or I'm sorry, the higher or taller it is, the more flexible it's going to be because of the space it has to dissipate that energy. For strength hierarchy, for a building to remain safe during an earthquake shaking, here's something very important for the building of your structure. The columns, up and down, should be stronger than the beams, and foundations should be stronger than the columns themselves. So your actual foundation, it has to be very strong. Strong columns, beams will come last. Okay. Next year I'm going to show you a video of a fellow that I think it was in San Francisco. Took a look at some earthquake-resistant design and some different features of particular buildings in San Francisco, but also on his very own shake table, showing us some things about these different structures.
Hi, Ms. Sakuta's class. My name is Hale Takazawa, and I'm going to give you a tour of San Francisco as we look at different buildings for lateral design that's going to help buildings keep buildings protected from earthquakes and other lateral movements. So lateral movement means you move side to side like this. And there's 3 different ways that engineers usually plan buildings so that they don't do that. Okay, we're here at Fisherman's Wharf, so let's go and look for some lateral reinforcement. We're looking for X braces or K braces like that. Okay, let's go. There's a big X. Tier 39. Now there's some bracing on there. See that? But that's not K bracing or X bracing, so it's just normal lateral bracing. Alright, so I'm here in my studio. This is my little playroom area. It has a lot of toys, you can see in the back of me, but it's good to model things as well. So today I'm going to show you about what we have been showing you, the K bracing, the X bracing, and no bracing. And this is my little earthquake table, and I'm going to shake it like this, and then we'll see which of these will stand up pretty well. According to engineering, I think probably the X brace and the K brace should do better than that, but let's see for ourselves. Let's give it a little shake. Oh, before I do that, there's Play-Doh. No, it's not brownies and it's not other things you might be thinking of. Bracing these things, and it's just stuck on there. You know, nothing special, but let's give it a shake. See what happens. Wow. Which building would you like to be in? Alright, well that's the idea, is bracing might break off, things might happen to the building, but it doesn't fall on the little guy that's standing there, right? This is an X brace between the trusses of the building and an X brace. See that X? We're here at the Exploratorium, and here we are, structural improvements for lateral bracing. Oh, an angle brace is part of a K brace. See how that angle is used on that structure? I have 2 towers, one with this cup with some counterweights on it, so when this shakes, hopefully the counterweights will help keep it stable. And on this side we don't have anything, which is a typical building. And we'll put our buildings to an earthquake. Voila! Don't stand close to falling buildings. Alright, here's Jet with a balancing stick at the top. It's the same principle we use for a building. Hold it on your hand like this, Jet. See if you can balance it. Just moving around like that. Whoa! So if Jet's hand is the ground and it's moving, move it around like this, Jet. Move your hand around like that. Yeah. That stays stable because of the counterweight on the top. Jet's hand is moving on the bottom like an earthquake, and it stays stable at the very top. Meanwhile, he's moving it like this at the bottom, and at the very top, nothing. A counterweight, just like you can put at the top of a building. Okay. Our last demonstration is, we'll go back to our little house construction with blocks. It's always fun. One side will be right on the ground. The other, we're going to put something called base isolators, Lincoln logs in this case. And it will be built on a foundation of rollers. This idea, I believe, was invented in Tokyo because the Japanese have a lot of earthquakes in Tokyo Bay. And this one is without. So we're going to put our little man down here. He'll probably fall down in a large earthquake, but let's try this. Very quick jolts here. Very quickly. These will happen and fall down. Alright, let's try this again. For a man who hits the ground. Right away, you get a big result. So these are the three types of countermeasures that you can use to keep your buildings from falling and keeping them a lot stronger. You have the K bracing, or you can also use X bracing, or you can use your base isolation, or you can use your counterweight up on the top. And if it's a counterweight that accelerates or moves differently than the ground shape, then the better off you'll be. And that's all I got to show for you today. Maybe next time I'll show you some other exciting examples of other things that we use as engineers. And my name is Hale Takuzawa, and I'll see you next time. Bye.